Okay, let's discuss reaction mechanisms. Essentially, chemical reactions, if you think about those, they don't occur in a single step, but sometimes they could occur in several steps. What I mean by that is just, to give you a flavor, let's say you're studying the reaction carbon monoxide reacts with NO2, gives you NO and CO2. Now, this can occur as NO2 plus NO2 gives you NO3 and NO. Then that NO3 reacts with CO to give you CO2 and NO2. And that's a fast step. And when you add both of these, you can hopefully see that the NO3 and the NO3 will cancel off. The NO2 and NO2 will cancel off. So you're left with CO plus NO2 gives you NO plus CO2. So an overall reaction essentially can be written as a combination of multiple steps. Okay, and essentially there are a couple things here. You will not see the intermediate steps that might be involved when you're seeing the overall reaction. So if you wanted to study, if you wanted to determine how exactly the reaction took place, you need to know what the reaction mechanism was. That's important. It's pertinent. So reaction mechanism is nothing but a series of individual chemical steps in which an overall chemical reaction takes place. And I gave you an example of this right here. Now, each of these steps that you write, irrespective of whether it's a slow step or a fast step, that is given a name. It's called as an elementary step. Okay, so one can say that many elementary steps together make up a reaction mechanism. So the mechanism is the whole deal, and each of these steps essentially is called as an elementary step. Elementary steps themselves cannot be broken down into simpler steps. They occur as they are written. They occur exactly how they are written. So that means that they will represent the exact species that is present in the structure. So for instance, if I'm saying that one NO2 reacts with another NO2 to give you the NO3 and NO, that is exactly that's happening in the test tube. Okay, so they are written as is. Now, realize sometimes, or if you notice, between the slow step and the fast step, one of the species, the NO3, that basically got cancelled off because the concentration of which is so little, it's so tiny that we are never able to measure it. And so for that reason, we use the word intermediate to define that. So intermediate species are those species that get formed in one step and then they get used up in subsequent steps. Okay. Now, as you can see in this particular case, if the reaction is run at high temperature, we have a rate law for that, in which we know that each of the two reactants, CO as well as NO2, are participating. They're important. On the other hand, if we run the reaction at a low temperature, essentially CO doesn't even feature in the rate law. That basically means that the order with respect to CO must have been 0. So that's the reason why it doesn't participate. So realize, by looking at the mechanism, by making certain measurements, you would be able to write down rate laws and hence be able to determine the order with respect to a certain reactant through writing mechanisms. How do we do that? The most important thing to realize here is the fact that when you look at the various different elementary steps that participate, that combine together to give you the mechanism, one of the steps is going to be the slowest step. And that slowest step is what is called as the rate determining step, sometimes also referred to as RDS, rate determining step. I mean, think about it. Let's say you're thinking about let's say you have a process, okay, a process that you need to accomplish over a weekend. The process is that you are applying for jobs, and so you ask maybe two of your friends to help you out, send applications to 50 different positions, and you want to send these the snail mail route, like a formal paper copy, not just an email. They haven't provided email, so you have to go the old school route. So the job is essentially to print out your CV, right? Fold it, put it in the envelope, and write down the address. And that makes one particular letter that can be mailed. And you have to do that 50 times. What do you think if this was a complete procedure and you wanted to kind of, put a time frame as to how quickly you would be able to accomplish the task? Hopefully you can see that everything, whether the job would be done in 2 hours or 3 hours or however many hours, the total amount of time is going to be dependent on how quickly the guy, whoever writes down the address and puts the stamp, because that's the slowest step. The other people are simply, printing, so that's print of a button, click. The other person, the second person, is just folding, putting in the envelope, and the third person is doing the writing part, which is what is going to take the longest time. So whatever is the slowest step is the step that decides, that determines how slow the overall reaction is going to be. So one can essentially measure the rate law of the rate determining step, and that will be equal to the rate of the reaction. Okay, so through the mechanisms, of course, earlier in the chapter we learned writing rate laws, and then essentially looking at the rate versus the concentration. So the various different experiments were picked and then orders were found. And then we learned about integrated rate law, in which I told you that the data given would be concentration versus time. So you're going to plot concentration versus time, see if it's linear, natural log of concentration versus time, see if that's linear, and 1 over concentration over time. Whichever is linear essentially tells you that it would be 0, 1, or 2 order, which essentially means that you're relying on these integrated rate law equations to figure that out. And this third method is following the mechanisms. And in order to get that done correctly, you have to locate the slowest step, because that is your rate determining step. Once you have determined which is your rate determining step, whatever is the rate of that automatically becomes equal to the rate of the reaction. I hope I'm ample clear on that. Let's go forward. So as I was saying, elementary steps together, many elementary steps together feed into a reaction mechanism. These are basically the individual steps that constitute a reaction mechanism. So these could be unimolecular, bimolecular, or termolecular. So you can characterize these by what is called as the molecularity. You can perhaps, just for a split second, you can compare molecularity similar to the order of the reaction. However, one thing that you need to keep in mind is that molecularity is specifically for elementary steps alone. All right, so molecularity is nothing but the number of reactant particles that are involved in a certain step. So you can say that if your reaction is A giving you B plus C, since there is only one molecule, one kind of molecule that is present here, we are going to call this a unimolecular reaction. On the other hand, if you have A plus B giving you A plus A or 2A giving you B plus C, that would mean that two molecules of A are involved, and so we'll call this a bimolecular reaction. So this could be of the kind where rate will be equal to Ka square, or this could be of the kind where A plus B gives you products, and so one can say that the rate is going to be equal to K times A times concentration of B. So both of those are bimolecular reactions. And the termolecular step would be if it's more than 2, that is if you have 3. Hopefully you can also see that the termolecular steps are going to be pretty rare, because it's going to be very difficult to have 3 different kind of molecules to come in and react together. So this is a rare event. Some other, reaction kinds one can write. If you have like 2A plus B, so A plus B is giving you products. That's 1 molecule, 2 molecule, 3 molecules. This must be a termolecular reaction. Likewise, if you have A plus A giving you products. Again, we have 3 molecules, and so we should call it a termolecular reaction. So really, all you have to do is count the number of molecules that are participating in the reaction, and that will give you the molecularity of the reaction. In this case, that reaction happens to be an elementary step. Now, as I was saying, I was talking about the rate determining step. Let's say my general reaction is A to D, okay? But that doesn't occur in one single step. It occurs through 3 different steps, that A gets converted to B, and it's a very fast step. B then gets converted to C, and that's a slow step, and then C ultimately gets converted to D. So this is a stepwise reaction, and if you add, you can see that the B and B will cancel off, the C and C will cancel off, and so you do get the overall reaction. But essentially, you may be able to picture that your slowest step is B going to C. If this is your slowest step, that means this is going to be your rate determining step. And for that, you can write down the rate of the reaction as K times concentration of B. And if that is true, then the rate of A to D is going to be approximately equal to the rate of B to C. All right, because everything else is a fast reaction. Rate of the reaction will be dependent on the slowest step possible. So again, if you had to deduce the rate expression from a proposed mechanism, your steps are, you have to look for the slowest step and write down the rate law and equate the rate of the overall reaction to the rate of that step. So let's see if we can apply that on something that we saw a couple minutes ago. I have an equation, NO2 plus NO2 gives you NO3 plus NO. Carbon monoxide reacts with that NO3 to give you CO2 and NO2. So hopefully you can see that the NO3 and the NO3 are going to cancel off. One NO2 is going to cancel off. When you add, this is your overall reaction. Now, your slowest step, these two, both of these are your elementary steps. And what gets cancelled, that will be called as the, you got it right, intermediate. So you should know how to identify what's what, okay? And the one step which is slow is basically your RDS. So if that is your rate determining step, hopefully you can see that you should be able to write down the rate expression for that step as rate is equal to K times, and then what are the reactants? We have 2 NO2s, so I'm just going to write both of those. And realize in this case I don't have to, I'm just going by the molecularity. I'm not worried about what the order would be, because realize only if it is an elementary step, which by the way is the simplest possible step, I can use the stoichiometry equivalence as is, only in case of the elementary step, nothing else. And that gives you rate is equal to K times NO2 squared. What does that tell you? That tells you that the rate of the overall reaction also would be same as the rate of the RDS. So the two are going to be exactly the same. So if somebody asks you what is the overall order of this reaction, you would say the overall order of this reaction is 2, because the order with respect to NO2 is 2. If somebody asks you what is the order with respect to CO, you would say it's 0, because CO does not feature in the rate expression. Sound good? So realize, even though we did not have a rate expression to begin with, we were given elementary step, we were able to deduce the rate expression, and hence we were able to determine the orders with respect to the two starting materials or two reactants that feature in the reaction, and hence we were able to determine the overall order of the reaction as well. So if somebody asks you now, which integrated rate law must it follow, or what should be the half-life, which one would it be? It would be, or would it be dependent on the half-life of, would it be dependent on, let's say, the value of K? Yes, of course. Would it be dependent on the value of initial concentration? Yes, of course. So realize that you can kind of place two and two together depending on the information that you're able to derive from one particular method. So to summarize, the elementary steps in the mechanism must sum to an overall reaction, and the rate law predicted by the mechanism must be consistent with the observed rate law. That's a pretty important point. Okay, and your dry lab will be a good practice for this. We already discussed what intermediates are. Intermediates are produced in one step and they are consumed in the later step. And the concentration is always just too little to be measured. And so these are usually eliminated from the rate expression. Okay, so when you're doing this, you must make sure that there are no intermediates, and the final rate expression must include only those species that appear in the balanced equation of the overall reaction, because it's the overall reaction that decides, what the real reactants are. So we are going to take a look at some of the ways that we can apply this information. The question is, find the rate expression for the following reaction mechanism. You're given that NO plus Cl2 gives you NoCl2, and that's a fast reaction. You're also given that NoCl2 plus NO gives you 2NoCl, and that's a slow reaction. You have to tell me what is the rate expression for this overall reaction. Now, you can say that the rate of overall reaction is going to be equal to rate of rate determining step. So if you are able to determine what the rate determining step is, we are going to take it from there. So which one do you think is it going to be, fast or slow? You got it right. It's the slow step, which is the RDS. So for that, I'm going to be able to write rate is equal to K times NoCl2 times NO. Again, notice I'm using the powers as 1 because these numbers are 1. And these are elementary steps, so the molecularity translates into the order. Now, if you look at your overall reaction, you do have an NO, so this thing I accept. Do you see an NoCl2? Not really. So we have to now figure out what NoCl2 is in a manner which is acceptable to us. Okay, so let's track NoCl2 down. We have it right here. It's getting formed in a reaction and then it gets used up in the next reaction. What does that tell you? That should tell you that it is an intermediate. That means the concentrations would always be too little to be measured. That is the reason that we do not want to keep it as is. So let's visit equation, the step 1. Let's visit that to see how we can get the value of NoCl2. Now, notice I have a double-headed arrow here. What that means is that this is an equilibrium reaction, that there is a forward reaction, which basically involves NO combining with Cl2 to give you NoCl2. And then there is a backward reaction in which NoCl2 is breaking into NO and Cl2. So it's a combination. Essentially, both of those are occurring whenever we have equilibrium. So let's write down what do we know about the forward reaction. So let's say it was rate of the forward reaction that we were writing. I would say that would be equal to K forward concentration of NO times concentration of Cl2. And if somebody says, if you had to write down rate of backward, that would be concentration of NoCl2. It's principle thing, and you will learn more about it in chapter 14, that if something is in equilibrium, whenever dynamic equilibrium exists, basically the rate of forward reaction and the rate of backward reaction becomes equal. What that means is that the Kf times NO times Cl2 is going to be equal to Kb NoCl2. One more time. What I'm saying, what I did was I took step one and I kind of dissected it as a combination of a forward and a backward reaction. I wrote the rate for the forward as well as the backward reaction. And then since in principle, the rate of the forward reaction, which by the way is the left-hand side of this equation, and the rate of the backward reaction, which by the way is the left-hand side of the second equation, if those two are equal, then the right-hand sides should be equal as well. And so you should be able to say, if you divide both the sides by, BS is for both sides, if you divide both sides KB, so we are dividing this by KB, essentially you would get KF times NO times Cl2 divided by Kb, and that will be equal to NoCl2. So we found a relationship over here, and hopefully you can see that you can plug that value into this first relationship of the rate law, and so your rate law will start looking like rate is equal to K times Kf times NO times Cl2 divided by Kb, and this whole thing is being multiplied by NO. So now you have three constant K, Kf, Kb, and if you basically have three constants, you multiply or divide them, you are going to end up with a new constant. Let's call that a K prime. You can consolidate the two NOs together, so hopefully you can see that that will look like a square. So this is now of the format rate is equal to K prime NO square Cl2, and that has a power of 1. And so the moment you look at this rate law, you already now know that the order with respect to NO is 2, and the order with respect to Cl2 is just 1. And so the overall rate order would be 2 plus 1 equals 3, and the constant K prime, which is a combination of the K, Kf as well as the Kb. The question is, which is an intermediate for the following multi-step? 2a plus 2b giving you c plus 2d. Notice there are three steps. E gets formed, E gets used up, F gets formed, F gets used up. So hopefully you can see that both E and F are going to be the intermediates in this particular reaction. Okay, let's solve another one. The question is, ozone naturally decomposes as two ozone molecules, giving you 3 oxygen, both in gas phase. The experimentally observed rate law is rate is equal to K times ozone to the power of 2, oxygen to the power of -1, and the question is, show that the following mechanism is consistent with the experimentally observed rate law. So hopefully you can envision what we have to do. I mean, if you think about it, what is given and what you have to determine, you have to say whether this mechanism is valid or not. So if by some method you are able to determine the rate law, okay, and that rate law ends up being exactly same as the rate law that was observed by observation by experiment, you can say that yes, mechanism and experiment, they go hand in hand, right? And so hopefully you can see that overall, if you think about the mechanism, essentially the oxygen and the oxygen being used up. So that is your intermediate right there. And when you add, you will have two O3s. So that's two O3s will give you two oxygens plus one, three O2s. So it does tally to be the overall reaction, but we have to basically now just simply prove it. So first things first, you would say that the rate of overall reaction is going to be equal to, and if you wanted to write the overall, you can do that again. So oxygen, oxygen cancels, 2O3 gives you 3O2. That's what we are trying to figure out. And I said that rate of overall reaction is going to be rate of the slowest step, the rate of the rate determining step. Since rate determining step is the slow step, we would be able to say that the rate should be equal to K times, and it's K2 times O3 times oxygen. Now, O3 by itself is acceptable. However, oxygen, nascent oxygen as in the atomic form is not, because that is an intermediate. This is an intermediate. So we have to get rid of the intermediate, then we have to write it in terms of ozone and oxygen. So how do we do that? Following the previous example, that's exactly right. So we are going to use the fast reaction now, and we are going to say that for the forward reaction, one could say rate of the forward reaction is going to be K1, or you can use KF, but since they have given me K1 and K inverse, I will kind of stick to that. So K1 times ozone, and likewise you would be able to say that rate of the backward reaction is going to be K inverse times O2 times oxygen. So since it's an equilibrium reaction, this is equilibrium, so we can say that rate of forward is going to be equal to rate of backward, and so one could say K1 times ozone is equal to K inverse times O2 times O. So you can simply say dividing both sides by K inverse and O2, and that will give you K1 times O3 divided by K inverse times O2, and that number will come out to be the concentration of nascent oxygen. I'm going to plug this number, plug this value of nascent oxygen into my equation. Okay, so it's going to start looking like rate is equal to K2 times ozone times K1 times O3 divided by K inverse times O2, right? And now we start consolidating. So hopefully you can see there are two ozones, so we can put a square there, and since K2 is a constant, K1 is a constant, K inverse is a constant, we will put all of that together as well. So rate is going to look like K2, K1, and K inverse. I'm going to give that a new constant, K prime times ozone. So there's two, I'm going to put a square, and realize the O2 is in denominator, so when you bring it in the numerator there will be a -1 power. Does that look any familiar to what you had previously? Rate and rate on the left side, there is some rate constant, ozone is to the power of 2, oxygen is to the power of -1. Aha, we have a winner. This is consistent with respect to the observed rate law. Does that make sense where we are going with this? Okay, let's talk about catalysis. Now, catalyst is a species that basically increases the rate of the reaction without being consumed by it. So what that means is that you will utilize it during the reaction mechanism, and in the end, by some mechanism, it's going to get generated again and be thrown back into the system. So a catalyst basically works, it operates by simply lowering of the activation energy. There are some molecules which actually inhibit certain mechanisms, and those are called as poisons. So catalysts and poisons are opposites of each other. Those are opposites of each other. Okay, now, like I said, it increases the rate of the reaction but is not consumed by it. There can be essentially two kinds of catalysis or two kinds of catalysts. One is called as a heterogeneous catalyst, the other is called as a homogeneous catalysis. Homogeneous would mean that your reactants and the catalyst, they are all in the same phase. So let's say you have a liquid catalyst, your reactants are liquid, it all becomes one gigantic solution, and you call that a homogeneous, or everything is in gas, you would use the word homogeneous. On the other hand, if you consider different phases, so for example, your reactants are liquids or gases, and the catalyst that you put in is a solid, you would use the word heterogeneous catalysis. So just to kind of give you like a flavor, catalytic converters that you see in your cars, the most expensive part really of the exhaust system, that costs like $800 or so. But the whole aim of that, since the late 80s, early 90s, cars are expected to have catalytic converters, because essentially before releasing the exhaust has an OCO, or rather, yeah. So the exhaust has NO as a gas. So when it goes through the catalyst, NO2, essentially it reduces the oxide as nitrogen. So what comes out, you have CO2, of course. So that's CO2, and nitrogen is given off. That means NO and NO2 are converted back to nitrogen gas. And it's successful, because it prevents or has decreased the amount of acid that would be generated otherwise by so many vehicles across the world. Because realize, if this NO or NO2 is released in the atmosphere and it reacts there with water, you're going to get the HNO3, HNO2, those are going to get generated, and they are components of acid rain. So this is a good way to prevent that from happening. Another example of catalysis would be, what is that? I cannot believe it's butter. So if you have like hydrogenation of oil, so oil contains double bonds, okay? Double bonds are called as alkenes. And essentially, if you wanted to convert a double bond into a single bond, you would have to put some hydrogen atoms. Turns out hydrogen gas is the least, in terms of mass. It's only 2 grams per mole, molar mass. So in order to get it to go, you have to provide a palladium catalyst, which provides the interface for the reaction to take place. So it lowers the activation energy by providing that interface for the reaction to take place. That interface is now going to be between the gas and the liquid or the solid, which is your substrate molecule. So again, catalysis could be of two kinds. It could be homogeneous, it could be heterogeneous, but the way catalysts work is essentially, by lowering the activation energy of the reaction. So one might envision that if you have a reaction which, you're drawing the energy profile, and you have the reaction progress, and let's say this is your reactant, this is your product, that's your transition state, and somebody asks you, what happens if you put a catalyst? Guess what? A catalyst is supposed to lower the activation barrier. So your activation barrier from here is much less as compared to what it was for the red curve. So that's what I mean by the lowering of the activation barrier. Okay, and so in this case, essentially the reaction will occur much smoother, much faster, because the activation barrier is now it has been achieved, it has been met. Now, another catalyst that you might have come across would be the biological catalysts. Biological catalysts, which are enzymes. And you know that enzymes are super duper specific for certain substrates only. Only when the enzyme substrate complex gets generated, the reaction takes place, right? So that binding is pretty critical for the reaction to take place. But if you think about the digestion process, you eat the food and it automatically goes through a digestion process. You don't have to provide the heat, you don't have to sit on a stove or something like that to make it go. It just occurs on its own. Why does it occur on its own? Because enzymes in your body are essentially responsible for that, and as the enzymatic action, as we might call it, as that occurs, essentially the food is digested and you are provided the energy for your daily routine. But either way, whether it's an enzyme or whether it's a protein that's getting you know hydrolyzed, or whatever the case may be, or the catalytic converter example, or the hydrogenation of oil, whichever example you think about, the reaction occurs through the lowering of the activation barrier, and essentially the enzyme it does not become a part of the reaction. It does participate in the mechanism, but then later on it does get regenerated in one of the steps. So you will see the enzyme or the catalyst show up on the product side at the end of the day. All right, let's concept. The question is, which is the catalyst for the following multi-step mechanism? So you're given essentially a reaction that has three steps, and you're asked which one is the catalyst. So notice B participates, it picks up G, gives you E. E is being used up, so that becomes your intermediate. This is your intermediate. It reacts with A to give you D and F. F gets used up, so that's your intermediate as well. And G gets generated in addition to C and D. So what do you think? Hopefully you are thinking what I'm thinking, that G should be your catalyst. Okay, so can I say that if G got used up and G got generated, basically its concentration is going to remain constant? Okay, so even going back to the rate law expression mechanism that we discussed a couple minutes ago, right before catalyst, realize that if you are given a reaction which involves a catalyst, since it's completely constant, it really would not participate in your overall rate law. Okay, just a thought that hopefully will be beneficial for those of you who would be spending some time on the upcoming dry lab.